run this computer. All right, cool. Okay, so let me start with something pretty simple. You can see the screen, right?
Yes, sir.
Okay. Okay, what should I give you? What should I give you? Yeah. Let's say you have an integral like this, dx e over x, x square. Any idea how to do this integral?
So applying the UV formula.
The UV thing or integration by parts? So if you apply UV formula like this, which one is easier to integrate? I mean, both of them are easier to integrate, right? But what you need to understand is that
EX is
if
more
you,
easier.
which one?
EX is more easier. I mean, EX will still
Yeah, but
be,
you can always integrate x squared to get x cubed by 3, right?
yeah.
But then what happens is that in integration by parts, you have something like this, like there is this f dx, some g over there, and then there is this f dx, and then you have some dg dx, right? And then you integrate this whole thing. So if you differentiate ex, it just stays ex and so on. So if you do it like this, let's say you want to integrate x squared first, so you'll have something like this, x cubed by 3 e over x, then differentiate e over x. That's just what? That's just e to the power x, right? Ex, and then you have this integral x cubed by 3 dx and this. And no matter how many times you differentiate e of x, that's just what? E to the power x, right? So these are the some sort of stuff that you need to look out for, because you see that in this way, this integral never gets exhausted. It will go on and on and on. So that's why what I can do over here is that I can just integrate over ex to get ex, keep x squared intact over there. Then I differentiate x squared to get 2x. There's the integral sign. I have my e over x and dx. And then what I can do, I can just integrate by part this thing again. So e of x, x squared minus 2 x e over x minus, what's the derivative of x? 1, right? With respect to x, obviously. And you have integral sign, you have e of x dx. Does this make any sense?
Yes, sir.
Okay. Any questions from this example?
No.
Okay, so let's try something different. Let's go back to that integral I think I discussed in both of your sections. This one, x squared plus a squared dx, right? And we wanted to have some sort of a substitute like this. X equals to a tan theta. So dx would be a sec squared theta d theta. Put this back into the integral. You have the following. Instead of dx, you have a sec squared theta d theta, and then square root a square tan squared theta plus 1. Okay, and then you have what? You factor out a's, all the a's over here. So this would be a squared. This is sec squared theta. And this is what? 1 plus tan squared is what? That's just sec squared, right? But then you have a square root. So you just have a sec theta and you have d theta. So eventually you will have an integral of what? Sec cube theta d theta. Now from now on, you can do some integration by parts so that you can at least reduce this into some convenient form. So if you observe this part, instead of writing as sec cube, what you can do is the following. Instead of sec squared, you know that tan and sec, they are pretty easy to integrate, right? So what you can do over here is that you can observe the fact that sec squared theta is just the derivative of tan theta, right? Like this. So what you can do is that you can integrate this sec squared and keep this sec theta alone. You just don't touch it at all, and then try to see in which direction this problem goes. So let's try that out and see what happens. So we will first integrate this sec squared theta d theta, and we will keep this sec theta alone. We won't touch it. If I integrate sec squared theta d theta, this is what? Just tan theta, right? Then you have integral sign and d theta. And now you need to differentiate sec theta, the one that you left intact in the first place. And then there is a multiplication of tan theta. And then you integrate this whole thing. What's the derivative of sec theta?
Tan theta.
Tan theta, are you sure? I don't think it's tan theta. What is the derivative of sec theta? Anyone?
Oh, oh. Sorry. I think it's sec theta tan theta. I mean
The
sec
sec
theta.
theta tan theta.
Yeah, it should be
Sec
sec theta
theta.
tan theta, right?
Yeah.
Still, let me check. I don't believe you people. Yeah, it's sec theta tan theta. I just used Wolfram alpha to confirm this. Whatever. Even I don't remember what was the derivative of sec theta. So there you go. So if this is sec theta tan theta, then you have the following. Sec theta, and then there's a tan square theta, right? Because tan times tan is just tan squared. Now we're still not done. We're back to square one. We're getting this secs and tans, and well, nothing makes sense. So what do? We can break down this tan, right? Because of this identity. So let's try to do that and see what happens. We can have d theta, and then you have a sec theta. Tan squared theta would be what? Sec squared theta minus 1, right? So then even close the braces. Then just do the algebra. Again, you have integration of sec cube theta and minus d theta of sec theta, right? Now let's distribute this a inside this whole thing and use this minus sign. I mean, the idea is to get rid of all these braces and see what happens. A square sec theta tan theta minus a squared d theta sec cube theta plus a squared d theta sec theta. Now this part is doable. I think it's what ln sec x, maybe, if I'm not wrong. You can prove it, like you can just go on and prove that this is some ln sec x or something. Is it right? There exists a very Nice formula for the integration of sec theta. Anyone? No? No clue? You know what? Let me just use the Wolfram just to
No, sir.
confirm my suspicion. Oh, these guys, they just kept thing in terms of ln. Okay, but this is doable, okay?
Sir, is it similar for cosec theta?
Almost. Yeah, you can directly integrate cosec too. Okay, but okay, just for now, you can do this, okay? Just keep that in mind that you can evaluate the integration of sec theta or cosec theta or so on. And I think the trick lies in the following. You write sec theta as 1 upon cosine, right? And now what you do is that you multiply some stuff in the numerator and the denominator so that the derivative of the denominator, sits at the numerator and stuff like that. So how do you do this? Well, this is one way. I think that you have to multiply by some cosine and sine. This is one way, but the other way I can think of is the following. You can write the sec theta as the product of this and this. You are multiplying some stuff like sec plus 10 in both the numerator and the denominator. And then if you want to integrate them, you can easily see that if you substitute this guy by u, this is your du, because the numerator now is sec squared theta plus sec theta times tan theta. And the denominator was what? Sec theta plus tan theta, right? The derivative of tan theta was sec squared and the derivative of sec theta was sec theta times tan theta. So if you substitute the denominator as u, the numerator is just du. So in return, you will have some ln of u, but u was what? Sec theta plus tan theta. So this type of integration of sec theta is just ln sec plus 10. That's it. So this guy is doable. But there is another interesting thing in this integral that we were doing is that you can see we started out with what? We started out with some x squared plus a squared, then we changed the variables, and that resulted in what? Some integration of sec cube, right? For example, if you want to add an extra line, it will look something like this. A square integration of d theta sec cube theta. Let's call this I for now. This integral, let's call that I. And on the right hand side of these arrows that I've written, you can see that there is another guy sitting that has the same face of the integral that you started with. So what you do right now is that's the following. You write a squared I equals to a square sec theta tan theta minus a square. This is what? This is I, right? This is something you started with, or it appeared in between when you change the variables. Does that make any sense? If it doesn't, you should ask questions. Does that make any sense? The thing that I'm doing. Let me mute myself for a minute and you should think and ask me questions.
Sir, for integration of cosec theta, will there be a negative sign before that or not?
Why it's tan x by 2? I didn't get that. Sir. Can you please explain? Oh, got it, sir. Thanks, sir.
হ্যাঁ সরি আমার এখানে আজান দিচ্ছিল তুমি তোমার কোশ্চেন অ্যান্সার পাইছো and do we have the international student who were with us in section 5 are you here
Yes, sir.
oh okay okay so the guy who was asking about the integration of cosec x dx you got your answer how to integrate cosec x and stuff okay cool now what you see is that there's another eye over there so let's resume what we were doing and finally we write this a square this integration was what ln of sec theta plus tan theta right well now as you can see this is one quantity and this is the same quantity and it has got a minus sign on the right hand side so what you can do is that you can take this quantity on the left hand side and so on also you notice that these factors they get cancelled out from both sides assuming a is not 0 so what you have at the end of the day is 2i equals to sec theta tan theta plus ln of sec theta plus tan theta okay so I is what I is just 1/2 of sec theta tan theta plus ln of sec theta plus tan theta and again I was what I was your this thing okay now up to this point we are done we have done the integration we have done everything there is no integral left but initially we did something initially we started with some x so it's better to switch back to x and stuff so if we want to switch back to x what was the substitution parameter like x equals to a tan theta right so tan theta was what x by a so this is my favorite method you can go other ways too if you want to find out the parameters tan theta is equals to x by implies to triangle or right triangle like this so sec means 1 upon cosine right so what is cosine cosine for this triangle would be what a by square root over x squared plus a squared so that would imply that sec theta would be square root over x squared plus a squared divided by a because sec theta and cosine theta they are reciprocal to each other that means sec theta is equals to 1 upon cosine and so on we already know about tan so we can just use these two pieces of information we can put them back into this result and get everything in terms of x if I do that the integral I or the result I will have the following format this would be x squared plus a squared divided by a times tan theta. So that's just x by a plus ln of tan was what? X by a. You can simplify it a bit further just by saying, oh, this is a and a, so this is just a squared and so on. But this is the real result in terms of the old coordinates or the coordinates that you started with.
Sir, can you please scroll a little bit upwards?
More?
No, sir. Thank you.
I'll give you the PDF, don't worry.
Sure.
I'll also get rid of this grid lines. It's just there for, I have a very messy handwriting. So even with the grid lines, you can see that my handwriting is quite a mess. So just imagine writing on this thing without any grid lines. Yeah, but do you understand the flow of logic? That's the most important thing. You can always check
Yeah.
back the calculations later. Okay, so now what I want you to do is that I want you to try this integral out. Instead of a plus sign, now you have a minus sign. So this is what you should try out and talk to me on Thursday. Might help you with the next homework. I don't know. I'll give you the next homework after I'm done with the definite integrals and stuff like that, so that I can actually give you some problems that would actually make some sense in your engineering applications.
Sir, I have a question relating these kinds of question. I mean, if it is given like this, or it is given in the denominator, should we consider this, like x is equal to a sine theta for both situation?
So you're talking about something like this?
Yeah.
You can put x equals to a sine theta. That's not an issue. But what you'll have is something like this. In the denominator, you'll have sine squared theta minus 1. So that's just negative cosine squared. You would have a imaginary number, and that's fine. You can do it, but there are some conversions. I think your answer will come in terms of this stuff, some logarithm stuffs. So you can keep the imaginary number. That's fine. But
Sure.
for example, there is this conversion. I don't know whether you guys know it or not. Sine of ix, where I is the imaginary number. This is sine hyperbolic of x. You can always convert them into hyperbolic functions. And hyperbolic functions can be converted to logarithmic functions and vice versa. Yeah, you can try this out. Yeah, but in this case, for example, this one, in this case, a suitable substitution would be either x equals to a tan theta or x equals to a cosec theta. If I'm sec squared theta minus tan squared theta equals to 1, right? So if I put x equals to a tan theta, then that would mean I will have tan squared minus 1.
So isn't it suitable when it is, x square plus a square is given, then we should suppose we should get x is equal to a tan theta when it is given plus?
That makes more sense in terms of not getting any imaginary terms and so on. In fact, if someone gives you something like this, you can just get away with saying x equals to a sine theta, because 1 minus sine squared is just cosine squared, right? No imaginary stuffs like that, no imaginary terms business. But yeah, in the case of a situation like this, x squared minus a squared, what would be a good substitution? You can even try x equals to a sec theta 2. You can try this out as well. In that case, in the denominator, you wouldn't have any
It's more
imaginary.
suitable, right? X is equal to a sec theta. I mean, using
I mean, I wouldn't say more suitable. The other things will work too, but you will have to deal with the imaginary number in front of your integral. And imaginary number in this case, well, you are not doing any contour integration over here, so that should be fine. I mean, the functional form of the end result can be different, okay? But you might think that sine of ix, you might think that this is some sort of imaginary thing, right? If you do a series expansion of sine, there are odd terms, and I over something odd will always come in terms of I, right? So you might think that, okay, this is something imaginary, but this is something not imaginary. This is something real. In fact, I over I is something real. I think it comes in terms of pi's and other stuff. So it's not an issue. It's not an issue. You can use any substitution you want. In that will simplify your integral, but then again, you'll just have to deal with the imaginary number and so on. That's the main thing. If you want to avoid imaginary numbers, then yeah, a sec theta would be a more suitable substitution. But if you substitute x equals to a tan theta in this integration over here, it would work as well. No issues at all. Does that make any sense?
Yes, sir.
Okay, so try this out. This integral over here, x squared minus a squared. Find a suitable substitution. See if you can simplify things, and then do some integration by parts to get the result. See if it works. If it doesn't work, that's fine too. Okay. Any more questions? If not, I'll show you another example that will involve the techniques that you learned in partial fractions and integration by parts. No questions?
No,
Everyone is tired? Okay, so let me find something interesting. This is boring. This is also boring. Boring. Oh, this one is interesting. I think this is the integral that's a bit interesting. Yeah. So there is integral like this: e over x. This is let's say 1 plus x, and this is x plus 3 whole squared. How will you do this? There is a rational fraction over here. So what we can do is that we can isolate out this e of x like this. Don't consider this e of x as a part of the fraction like this, because e of x is well, if you want to have a Taylor series expansion of it, this is a polynomial with infinite terms. So whenever you involve this e of x into the numerator, it's not a rational fraction anymore. But if you say, oh, this is some f and this is some g, then this g function or this fraction can be thought of as a rational fraction. And whenever there is a rational fraction, you can just simplify it by using partial fraction techniques that you learned in the previous class. So can anyone tell me, how do I decompose this thing into partial fractions? Anyone? What will be the terms on the right hand side?
So a by x plus 3
A by x plus 3, okay,
Whole square
plus
whole squared. Then
plus
bx plus c.
no sir, not
No, no.
bx. X
Oh,
plus
no,
3 is just what? A
just a
first
number.
degree polynomial, right? So this
or
second term
a
would
by
be,
x plus 3.
it's just b by x plus 3.
Oh, yeah.
Now the rest of the job is pretty simple. You just multiply stuff. Okay, I'm skipping a few steps. You should fill them out if you feel confused. Okay, or you can ask. I'm doing this just to be, quick. So what does this imply? This implies a plus 3b equals to 1 and b equals to 1. If b is equals to 1, then a is equals to minus 2. Then 1 plus x divided by what? X plus 3 whole square can be written as follows. This is minus 2 divided by x plus 3 whole squared plus 1 by x plus 3. Something like this, right? Does that make any sense?
Yes, sir.
Sure.
Yes, sir.
Okay. So our integral will look like the following now. This is d of x, e of x minus 2 x plus 3 whole squared plus 1 by this thing. Now you should distribute the integration measure with all the ingredients. Oh, there's a 2 as well. So x plus 3 whole squared minus dx e of x x plus 3. Now we don't know how to do this, right? Try anything, it won't work. You can try u substitution, v substitution, whatever substitution, trigonometric substitution, it won't work. Even integration by part won't make any sense. But if you take this term, then there might be some hope of, you know, actually evaluating this. Okay, that doesn't make any sense, right? I mean, does that make any sense, or that doesn't make any sense? No one
Yes,
is
sir.
responding, so I don't know. Is it going over your head? Yeah, I don't know. But can someone check whether this thing actually gives back this guy? Can anyone check this? Let me check this. No one is. I think people are tired in general. I don't know. This is 2 and this is x plus 3. So yeah, this is right. Okay, so our calculation was good. All right, so what you can do right now is that leave this part out alone, because if you try to integrate by parts of this thing, you know, if you try to integrate this thing by part, you'll just see that it's not going anywhere. You will have x plus 3 whole cube, x plus 3 to the power minus 4. Terms like this will continue to grow and stuff. But if you try to integrate this guy, there is a value in that. So let's try to figure that out.
প্লাস হবে না?
Plus y plus. Oh, it should be a plus sign. Yeah, thank you. So there's a 2 over here, dx e of x x plus 3 whole squared. Now you integrate by parts. If you integrate by parts, let's integrate e of x so that I can only have a e of x. I leave 1 upon x by 3 alone. Then I differentiate 1 upon x by 3, which in turn there is a minus sign over there by default. And when you differentiate 1 upon x plus 3, there is another minus sign. So these two minus sign will result in a plus sign, and the denominator will have a x plus 3 whole squared, and the numerator is e of x, right? Does that make any sense? We're able to, you know, grasp all those things that I said regarding this calculation, this line? No?
Again, please.
So you are now integrating by parts, right? You are integrating things by parts. So when you integrate things by parts, well, what do? You pick up one of the functions, you integrate them, leave the other one alone, and then you put a minus sign, and then you differentiate the function that you first left intact. In this case, we are first integrating over e of x, right? And we are leaving 1 upon x plus 3 alone. We are not doing anything to it. But then there's a minus sign, there's an integral sign, there's this dx, but then we need to do what? We need to differentiate x plus 3, or 1 upon x plus 3 in this case. So you are differentiating 1 upon x plus 3 like this. Sorry. This is just minus 1 upon x plus 3 whole squared, right? Now, do you get it?
Yes, sir.
Okay. So yeah, that was the thing. And now, well, just put this parenthesis over here. And what you can see right now is that we are almost close. We are almost close in doing this integral, but there's another issue. There's a -2 over there. Otherwise, these two things are the same. One has got a plus sign, other's got a minus. If it were something like this, 1, then we would be done. But it seems like we have to do a little bit of more calculations to get this thing done. So what do you do in the next step? Well, this is a plus sign, so just forget these braces right now. One of this integral over here will cancel one of these contributions, right? Because there's a -2 in front. So in total, you have a minus d of x, e of x, x plus 3 whole squared, plus e of x divided by x plus 3. Something like this. Does that make any sense?
Yes, sir.
Okay, cool. And what to do? What to do now? We cannot touch this guy because there is no integration over there, right? And if you try to integrate by part this thing, you know, if you want to apply this integration by parts techniques on this guy, see what happens. Let's try to do integration by parts of this guy. You integrate e over x, you have x over 3 whole squared, then you have a minus sign, you put your dx e over x, and you differentiate 1 upon x plus 3 whole squared, right? So that would give you a minus sign or -2 over there and x plus 3 whole cube. Then again, it's no good. You can just keep this term. You integrate by part this guy again, dx e of x, x plus 3 whole cube. You know what? Let me just keep the minus sign and -2 over there. You can again integrate by parts by saying, oh, if I integrate by parts, there's nothing good over there. You'll just have e of x, x plus 3 whole cube, -2. And then there's a minus sign, dx e of x -2. But now you'll have another -3, and in the denominator, you'll have a power 4. And you can easily recognize that this integration will never get exhausted. So this is the most simple form that you can keep for this type of integrals. And why am I showing you this? Because there is a thing called reduction method. When we do definite integral, you will have to use these methods. The idea for this type of integrals is the following. Let's say you have an integral, and let's say it's this. You guys are familiar with recursion relations, right? In your CSC wanted, maybe you have seen something. The value of something depends on the previous value of the other thing. So these are those type of integrals. In this case, the value of the n plus 1 recursion, or the, you know, on n plus 1 recursive step, it will depend on some I of n or I of n minus 1, stuff like this. This type of integrals you cannot do by hand. You'll have to render to a machine to solve it numerically. So that's why I wanted to show you this example. But what you can do in your home is that instead of x plus 3 on this problem, instead of x plus 3, try x plus 2. And you will see that on this step, on this step, these two will exactly cancel each other out. And in that case, you will have a finite result.
Sir, what should be the result of this math?
Oh, this guy.
Yes, sir.
And on the left hand side, this red box, you cannot exhaust it. It will go on forever, no matter how many
So-
times you integrate by
So
parts.
there is no answer for this.
There is
question?
answer for this. There is
No.
answer for this. The answers will always be approximate. It will never be exact. There is
No,
no
sir.
what you want to say is that there is no analytical result, or there is no analytic function, or there is no closed form. There
Yes,
is no,
sir.
yeah. So this is something you will see in the reduction, which I think I can cover in the, well, next Saturday, after I'm done with the improper integrals and stuff like that. Yeah. You guys are doing labs, right? And in your labs, have you seen this type of thing where the value of one integral depends on the other?
Sir, we have done only one lab and
Yes, sir.
we only
Not yet.
got the
So we
basic
have
of
learned just the
Python.
syntax of the Pythons. No, we didn't touch the maths.
Yes, sir.
Oh, syntax. Are you
Yes,
using
sir.
NumPy?
We just learned the sir syntax of the Python because sir in Tripoli we didn't get any Python code courses earlier. That's why.
Oh, okay. Okay, cool. Okay, nothing to worry about. Don't worry about these things. Okay, somebody called. I don't know who. Give me a second. Okay, so let me show you another example. You can solve this exactly. How about which one? Which one is a bit interesting? Most of the integrals are boring, like the ones, I mean, most of you have seen it. So there is no point in showing those stuffs to you. Okay, so this is easy. This is also easy. Okay, how about this one? E of x, sine of x, dx. How would you proceed? Any idea?
We can use the UV rule here.
Okay, but which one would you integrate first and which one would you differentiate?
Sin x first.
You want to integrate sine x first. And then differentiate e of x, right? That was the idea. Okay, in this case, it really doesn't matter because sines and cosines are, they're just, if you take a derivative of sine, you'll get cosine, and if you take a derivative of cosine, you'll get sine. And e of x doesn't change under derivative, so no matter what you do, it's fine. Okay, so on the left hand side, we have what? E of x, sine of x, dx. I want to integrate e of x, keep sine of x as it is. Then if I do integration by parts, this is something I end up with. I'll not write this, I'll just use some dot dots to indicate that this is there. You can now integrate by part this guy. You can just do integration by parts again. So if you do integration by parts again, it will be e of x cosine of x. There will be a plus sign. So fill out these details. I'm not writing them explicitly. Do you think there will be a plus sign or there will be a minus sign?
Sir, plus sign.
No, there will be a minus sign. Just because I said plus, that doesn't mean it will always be a plus sign and stuff. Because look, first of all, think of this guy as an individual thing. One of the minus sign is coming from what? The definition of the integration by parts, right? And the other minus sign is coming from the derivative of cosine x, which is just sine of x. These two minus sign will produce a plus sign, but since there's another minus sign in front, in the end, there will be a minus sign over there. And it will have something like this: t of x, e of x, sine of x. And this is equals to what? The integral that you started with, right? So take this guy on the left hand side, and now you will have 2 e of x sine of x dx equals to e of x sine of x minus e of x cosine of x, or e of x sine of x dx equals to 1/2 of e of x sine of x. This thing. What you should do in your home is that try to use the similar steps and evaluate a of x sine of b of x. Try to do this thing. And if you're familiar with complex number, this is pretty easy. Let's say you can write e to the power I theta as cosine of theta plus I sine of theta, right? And e to the power minus I theta as cosine of theta minus I sine of theta. So from there, you can conclude that sine of theta is just e to the power I theta minus e to the power minus I theta divided by 2i. Now you just plug this back. Instead of theta, you have b of x, and then you multiply stuff and treat this I as a constant. If you do that, this becomes far easier. Or you can just integrate by parts. So this is one of the exercises that I wanted to do, just so you really understand what you're doing. Then there is e to the power mx cosine of nx. This is another thing I want you to do. These are some exercises. If you get stuck, you can always post it in general or talk to me after the class. Okay. So that's pretty much it about, integration by parts. So any questions so far? You just have to figure out like which function is easier to integrate and which one is convenient to differentiate. It's all about convenience, reducing down the functional forms. So if you, yeah,
Do we have any quizzes in the next week?
sorry.
Do we have any quizzes in the next week?
No, you don't have any quizzes in the next week. I mean, I can take one quiz. What is today? Like 11th, right? So this is week 3. No, not this week, but in the next week, like let's say next Thursday, not this Thursday. And if I take a quiz on next Thursday, then I think I'll give you another assignment within a few days. So it will be based on assignment 1 and 2. Or maybe I'll reduce the syllabus. I don't know. I haven't decided anything on quizzes yet. Don't worry about quiz or exams or stuffs like that. I mean, in quiz, I'll not, give you some integrals like this that you'll get confused in the midway. Just try to learn the things.
So I was asking this because maybe I might have to miss a class on this week.
Oh, that's fine.
That's why I was asking.
Yeah, that's fine. That's absolutely fine. Missing one class wouldn't hurt much. I mean, I'll just show you some definite integrals. You guys are already familiar with all the techniques of indefinite integrals. In definite integrals, there is just, limits. After you integrate, you put in some numbers inside. That's it. So before I move on to definite integrals, do you have any question from integration by parts? Any questions at all? No? No questions? Should I move on to at least, I think I can cover the theory at least and show you 1 or 2 examples. Should I move on to definite integral?
Yes, sir.
Yes, sir.
Okay. So this is when we give some meaning to integration in definite integrals. So the idea was to compute the area under the curve. What do I mean by that? Well, let's say you have a coordinate axis like this. And now you have a curve. This is some, some nice function, let's say some f of x. The problem was to compute the area under this curve. Let's say this is a point A and this is a point B. The problem was to compute this area. So if you put it mathematically, then this translates into that you need to find the area under the curve under a certain interval. And in this case, the interval of interest is just between A and B. That's it. Okay. So how can you do that? Well, the idea that I'm going to share right now, this is called the Riemann sum or the Riemannian method. There is another way. It's called the Lebesgue. I don't know the proper spelling of his name, so I'm not going to write it. So there were two solutions of this thing. One was the Riemann summation formula, and the other one was a Lebesgue summation formula. So now this is your region of interest. You have marked that. What you can do is that from Euclidean geometry, you know that if you have a rectangle like this, if it's if it has a length of L and a width of B, then the area of this rectangle would be L times B, right? So the idea was the following. You just imagine some rectangles like this. From the beginning to the end. And obviously this vertical bars over here, they will intersect or intercept, whatever you want to say, the x-axis into certain points, let's say A1, A2, A3, A4, and so on. And from this drawing, you will see, oh, there are some regions left like this, So their idea was that once you take this interval, let's say this interval from A to A1 to be very, very, very small, that means they're approaching each other such that the difference del A, let's denote that as A1 minus A, it will tend to 0. That means it's very close to each other, this thing. Slide it over on the left side. In that case, you will have infinitely many rectangles inside this curve under the interval of interest. And in this way, you can actually get a very accurate result. By accurate, I mean exact, because initially from this drawing, you will see there are some regions left, right? You don't want to leave these regions out. So that was the idea of the Riemann summation thing. Now, how do you do it? Well, let me draw this picture again. Let's assume that we have successfully somehow drew this infinitesimal rectangle. Can anyone tell me what is the length in this case, or width? This is x, this is y. And obviously y equals to f of x, right? Can anyone tell me what is the length of this rectangle? By length, I mean the largest arm. Which is the largest arm? Or how do you know which is the largest arm in this case? This is the largest arm of this rectangle, right? So if the width is infinitesimal, That means this guy, del A, this is infinitesimal, by the way, very close to 0. Then to a very good approximation, you can say that the length of this arm is just f of x. Does that make any sense? No?
Explain that again.
Okay, so think of this rectangle, right? So take any point in this curve. What is the y coordinate of this points, in terms of x? Let's say I want to take this point. What is the y coordinate of this point in terms of x? Well, let's say if I only know x, can I get the y coordinate of this point? This point will have two coordinates, right? One is x, another one is y. So let's say this point is A, and I only know the x coordinate of this point. Can I find out the y coordinate of this point? I can, because I know the function,
Yeah.
right? So my idea was that if you construct a rectangle like this, let's say between 2 points, let's say this is one and this is the other, A1, A2, or you can also call them x1 and x2 if you want, x1 and x2. This is not entirely a rectangle, right? If you want to construct a rectangle, you need to leave some part out. But we don't want to do that. We want to be accurate, right? We don't want any errors and stuff like that. So what we do is that let's call this line, let's give it a name, let's say P. We move this P on the left side to such an extent that the difference between these 2 points, they tend to 0. And we call it del x. So once this difference between x1 and x2 tend to 0, you can approximately say that these 2 lines will be very close together, right? And since they're very close together, sorry. Let's say this is a very zoomed in pic. The coordinate of this point over here and this point over here, these 2, they will be approximately the same thing. And how do you find that coordinate? Well, y equals to f of x, right? So this rectangle will have a length of what? F of x, because y equals to f of x, right? This is what? The distance of this point over here, this point from the x-axis is represented by what? The y coordinate. But y is coming in terms of x as a function of x, right?
Yes, sir.
So that's why I'm telling you that the length of this arm will be f of x. That was my idea. And the width is just del x. Now, let's say this is our interval, from A to B. We can construct many rectangles like this, right? As the distance between 2 points grow very close to 0, the number of the rectangles will be infinite. So by infinite, I mean very large, not that infinite that you guys write as 1/0 or something. So the area under that curve can be written as the summation. Del x, but sorry, I forgot to write the limit. This is the original thing, and you will use this in Python because the machine won't. If you use NumPy doesn't understand anything rather than numbers, so you'll need to use this, and you will see that as you decrease the distance between 2 points, that means the more you split up the interval, the accurate the result will get. So this was the area under the curve problem, and what people did is that when they said that, oh, when this del x goes to 0, instead of discrete rectangles, you will have a continuous set of rectangles. So then they replaced it with integration. And you have the lower limit and the upper limit like this. Why the lower limit goes on down below and why the upper limit goes on on top. Well, this is a convention. And how do I know what is the lower limit and what is the upper limit in this case? How can I say, oh, why don't you just write B as the lower limit and A as the upper limit, right? It totally depends on the problem. I mean, yeah, because I wanted to start out from left, if I want to start out from left, if I go like this, and construct rectangles to fill up the area under the curve, then I'll say, oh, I started out at point A and I ended at point B. So the difference would be what? Some sort of a B minus A, right? On the total interval. So that's how you determine lower and upper limits for an integral. It all depends on which point you start with, or which is your reference point, and which point you end with. The point you start with, or the reference point, is your lower limit, and the end point is your upper limit. And how do you evaluate this? Well, let's assume this is some capital X, capital F of X, by which I mean is that, if you have f of x dx, the indefinite integral would give you this thing, C, let's say. Now, this is arbitrary, but once you have the lower limits and upper limits like this, what you want to do is that you want to compute the value of this quantity at these two extremas, or these two boundary points. Because if you see the interval, they are like some sort of boundaries, where you start things and where you end things. So in general, what people do is that they write down these limits. They put a third brace, and put the limits like this and write f of b plus c minus f of a plus c. And then you write f of b minus f of a. If you want a detailed proof of it, I suggest you check this in Riley-Benz-Hobson book that I gave you in chapter 2. It's called Preliminary Calculus. There's a detailed proof of it. And if someone wants a more mathematical detailed proof, then they should go for Stewart's calculus. There's a detailed proof of all these things. So the punchline is that if you have a definite integral like this, sorry, PA, you evaluate it like this. Okay. In physical problems, whether you get the correct result or not will solely depend on how you set up the limits over here. If you set up the limits right, you will get the right result. If you set up the limits wrong, you will get the wrong result. I mean, the result will be right, but well, you will miss out a minus sign. In fact, what you should check is that using this definition of definite integral, let's say I'm giving this to you, what you should check is that this thing holds. You can just show this by using this result in the blue box. Okay, does that make any sense? Any questions about definite integrals? No, everyone is confused, I guess. So I think I should leave you. You guys are exhausted from university and stuff. But before you go, just say this. Let's say I have integral from -2 to 2. For now, this is a very simple one. X of n dx, let's say. So everyone knows how to integrate this thing, right? This is just xn plus 1, n plus 1, and 2 and -2. After you're done integrating, the indefinite integration, you just need to put the values of the limits inside this. So the first thing is you see that the upper limit is what? 2. So this is 2n plus 1 divided by n plus 1. Then you put a minus sign. You write this whole thing, but this time you use the lower limit. So this is minus 2 over this. So the resultant thing is just 1 upon n plus 1, 2n plus 1 minus 2 n plus 1. You just put in the values. That's it. That's how you do definite integrals. You can now even try to show that. In fact, this is something you should try as well. Let's say this is 5 minus 5 and 5. Sine of x cosine of x. If I'm not making any mistake, this should be 0. In fact, are you guys familiar with even functions and odd functions? No? Okay. You know what? This is enough for today. I don't want to torture you anymore. Yeah. So this is where I'll stop right now. But if you have any questions, you can ask. I'll talk about this stuffs later on Thursday.
Yes.
Any questions? No? So everyone's good, I guess?
Yes.
Okay, that's cool. Maybe I should call up another virtual session somewhere in between this week because I missed like what, 3 classes in total. So I should take the makeup classes, right? If I take any makeup classes, that will be virtual. It won't be physical. I don't want anyone to come to campus if they doesn't have class or something. Okay. All right. So what you need to do right now is that you need to practice those integration by parts thing. And if you understand indefinite integration, definite integral will be a walk in the park. So don't worry about these things. However, when you set up a physical problem, you know, the problems that actually matter or what you guys call applications, in those cases, you will have to be very careful in taking the limits. You'll have to understand the problem, what you're doing. If you don't understand that, then you won't be able to set up the integral or, you know, determine the limits and stuff like that. For example, in these 2 silly examples, I have given you the limits, right? In those cases, the limits won't be given and you'll have to figure them out for yourself. But those are, you know, those will come in later and stuff. So don't worry about it and don't sweat about it right now. Okay, so any more questions before I turn off the recording and, you know, call it a day?
No.
Okay, thank you.
Sir.
Yeah.
আপনি